Welcome back. This is 3.3, which is graphing using intercepts. So we have seen intercepts before, but we're going to kind of use them, we're going to exploit them to graph a little bit. So let's take a look first and foremost at what these intercepts are, what we mean by an intercept. On a graph, let's say I have a graph of some function, some relation, doesn't even have to be a function, so it could just be anything. It's just something that is graphed, right? Whatever happens, you have something going on, right? Every time that this function, or this, sorry, it's not a function, this is clearly not a function, but this graph, every time it crosses over the x-axis, here, 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 those are all x-intercepts. They intercept the x-axis. That is to say that they don't have a y value. They do have a y value, it's 0, right? And so every time that the graph has a y value of 0, we say that that's an x-intercept. So x-intercept is when y is equal to 0. We also have a couple of times that we cross over the y-axis here, right? Those are the places that x is 0, and those cross the y-axis, so the y-intercepts are where x equals 0, right? So we have those two bits of information, and we can exploit those in straight lines, because with a straight line you've got at most two intercepts. You're going to cross the x once, you're going to cross the y once. Not all the time, we'll see that is not always the case, but we're going to dive into this and exploit these and graph a few functions with them. Okay, so let's take a look at perhaps this function, and this is very useful in standard form of equations, so we're going to start with those. I have something like, say, 3x plus 4y equals 12. Okay. And if we're trying to graph this, it's very easy to come in and say, hey, what happens when x is equal to 0? Because if x is equal to 0, this whole term right here is 0. And it's gone, it disappears on me. The only thing that's left is this 4y equals 12. And it's really quick and really easy to figure out what y is in this case. It's 3. Right? So that tells me when x is 0, y is 3, and it took very minimal effort to get that information. Right? That's one of my points. Now if I then also say what happens when y is equal to 0, if y is equal to 0, then this other bit is 0 instead, and I'm just left with the 3x part. So it's just 3x plus 0, so it's gone, is equal to 12. And again, it's very quick, very easy to figure out that x is 4. That is to say, I have the point x is 4 when y is 0, so the point is 4, 0. And this is a straight line, so that's all I need are these 2 points. Once I have 2 points on a line, I have the whole line. So I can graph this with just that knowledge. Okay, so I can take this and let's get a graph here. I have the point 0, 3, so that's 0, 1, 2, 3 is right there. And 4, 0, so 1, 2, 3, 4, and that's all I need. Those 2 points, try to create a straight line. That's probably as straight as I'll ever get. But that's my graph right there, right? That's it, I'm done. Quick, easy. Let's take a look at another one. Let's look at 2x minus y equals 4. So again, I should be able to come in here and say, if x is 0, what happens? Well, then this whole term is just 0, and I end up with just minus y equals 4. And if you divide both sides by -1, we end up with y is equal to -4, giving me the point 0, -4. And then if y is equal to 0, then this middle term is gone, the y is gone, so it's just 2x minus 0, which is just still 2x, equals 4. If we divide each side by 2, then we can see x equals 2, giving me the point 2, 0. Again, with almost no effort, all I did was throw in zeros, which throws away a term. I have 2 points, that's all I need because it's a straight line. And so, my graph. At the point 0, -4, that would be here. The point 2, 0, that would be here. And ideally when you're graphing this, you have some sort of graph paper. When I graph on this board, it's terrible. My lines are never straight. My units are never equal. I'm terrible at drawing these on the board. So hopefully, take a moment and draw a nice one on a graph paper. But here we go. That's my graph. And I'm done, right? It's quick, it's easy, right? This is ideal when the numbers in front of your x and your y can both divide this last number, as you'll see almost all of the examples in this section do. When they don't, then we're going to go on to the next section and see what to do about that. But here we are for now. All right, let's take a look at one more of these. Let's look at 2x minus 5y equals 10. Again, you notice 2 and 5 both divide 10. That's what makes this kind of nice, gives you nice integer intercepts. But if x is 0, we're left with just -5y equals 10. Right? If we divide both of these by -5, we're going to end up with y is 2. -2, excuse me. So I have the point 0, -2. Okay, I know I've got that. If y is 0, that gives me 2x equals 10. Divide each side by 2, x equals 5. So I have the point 5, 0. Make sure you get the x first. Right, get those ordered pairs in order, or else they're not ordered anymore. And then it's a quick graph. At the point 0, -2, call it there. At the point 5, 0, there. A line, and I'm done. That's it, right? Again, that's the whole idea of this section, is to show how quick and easy it can be to draw a graph like this. After you've done a few of these, you'll get to the point where you can just avoid actually writing the material down, the math down, and just graph it. So like, for example, if I have 3x plus 5y equals 15, is this one we did? Nope. All right. I can just reason my way through it. After I've done a bunch of these, I can say, well, what happens if x is 0? If x is 0, divide this by 5, I get 3. 1, 2, 3, there's my y-intercept. What happens when y is 0? Well, that term is gone. I get 3x equals 15. Can you see that? My arm's in the way. Divide each side by 3, and you get x equals 5. 1, 2, 3, 4, 5. There it is. There's my line. And it took me, 20 seconds to not only do it, but explain it as well. Right? So that's the idea, is that you can get to this point where it's quick and easy. Right? It may not be for the first couple. Don't freak out if you have to think about it for a little bit. But this is the idea, is to just get to the point where you can just whip it out and you don't have to write a whole bunch of math to justify it. All right, let's look at a couple more equations though, because so far we've had everything work out nice for us. The first not awesomely nice example I want to talk about is, what if we have something that's y equals, I don't know, let's say 2x. Right? If I let x equal 0, then I get y equals 0. And that's a point. I have the point 0, 0. Right? But if I come in and try to do the same thing that I've been doing, and I say, hey, let's let y equal 0, well, that's 0 over here, that gives me 0 equals 2x, but if I divide by 2, I still get x is 0, oops. And that's not a new point, that's the same point. X is 0, y is 0, that's the same point, right? So I don't have anything to help me out here with the second point. All I have is that I have an intercept at the origin. In fact, that's both my x and my y intercept, is when it goes through 0, 0. So I have to just backtrack and say, well, that doesn't help me out much, so I have to pick something else. And you just pick anything. In this case, I can say, well, that's not helpful. Well, what happens when x is 1, right? And if x is 1, then I get y equals 2 times 1, or y equals 2, and I simply have another point, 1, 2. Right? And let's graph this and see why this did what it did. I have the point 0, 0, that's here, and I have the point 1, comma 2, so 1, 2 is there, and that line, there is no other place that this line crosses the intercepts, it's only there at the origin. It crosses both the x and the y-axis, so you're never going to get another spot, right? So if that is the case, if you end up getting the origin, you just have to step off of it and try something else. Okay. So that was the first weird example. That example was when your x and your y axes were your x and your y intercepts were the same point, right? We might have something that looks like this though. Here I can say what happens when x is equal to 0. If x is equal to 0, who cares, because x isn't in this equation. Y is equal to 2, that gives me a point 0, 2. We're good with that. But if I come in here and say, hey, what happens when y is equal to 0? I get 0 equals 2. Well, that can't be, right? Nope. So y is actually never allowed to be 0, which tells us that there is no there's no x-intercept, right? But we've seen this before. Y equals 2 is just a horizontal line. At 2, it's just this line that goes through 2, right? There is no x-intercept because it's it's parallel to the x-intercept. And so it'll never cross, it only has one intercept, and it's the y-intercept. And it just happens to be at 2, because it's 2 everywhere. And of course, since we have a horizontal line, we could also play around with a vertical line. If I have, say, x equals 2, I can't say, well, what happens when x equals 0? Because then that means 0 equals 2. That doesn't happen, so x never is 0. Which means I never have a y-intercept, right? But we know this if we looked at the graph. X equals 2 is a vertical line at 2. It's never going to cross the y-intercept, right? So it has one intercept at 2, 2, 0. And that's it. It doesn't have a y-intercept. So those are the three weird kind of lines. The rest of them though should look like the first couple that we did, and you should be able to find two intercepts and graph a line on them. Thanks, we'll see you for 3.4.